let us discuss this example. So in this example, we have a set U and we have to prove that it is open subset of R2. See, if you see the definition, it shows it is a region bounded by two lines, x plus y is equal to 1 and x plus y is equal to minus 1. So I will clearly mention here U is a region bounded by x plus y is equal to 1 and x plus y is equal to minus 1. It is a region bounded by these two lines. Okay, you can see here. So we have to prove that it is an open set. To prove that U is open in R2, obviously with Euclidean metric. So what is our technique? We take one arbitrary point, okay, and we find a radius, okay, such that that point with that radius, that ball will entirely lie inside U. So let P is equal to P1 comma P2 belongs to U be any arbitrary point. Okay, I will show in a diagram. Suppose this is point P. Suppose this is point P, which lies inside this set U. So therefore, this point P will satisfy the definition. Getting? So minus 1 less than P1 plus P2 less than 1. Getting the point? So therefore, minus 1 less than P1 plus P2, comma, P1 plus P2 less than 1. I wrote the same thing, but I split in two inequalities. Getting? Minus 1 is less than this one and P1 plus P2 is less than 1. But we want something greater than 0. So that's why we shift 1 on that side. So therefore, 0 less than P1 plus P2 plus 1. Getting? If I shift minus 1 on that side, and here what will we have? 0 less than 1 minus P1 minus P2. Yeah, we got some positive real numbers. I will divide both sides by 5. Tell me what will you get? Therefore 0 less than P1 plus P2 plus 1 divided by 5 and 0 less than 1 minus P1 minus P2 divided by 5. Okay, then whatever the minimum of these two, that will be my R. Minimum of P1 plus P2 plus 1 divided by 5 and 1 minus P1 minus P2 divided by 5, whatever will be minimum, that will be my R. Clearly R is greater than 0, since both of them are greater than 0. Already we have written. Getting? So their minimum is also greater than 0. It's a 100% positive real number. Now our task is to prove open ball with this center P and this radius R will entirely lie inside say this U. Okay, so this point center P and this radius R will entirely lie inside this set U. This thing we have to prove, but there is no more space. So I suggest you to make a screenshot of it. After that we will go further. But instead of 5, what will I do? I will take 2 here. It is better to take 2. If you take 5, no problem. But if you take 2, then also it will be okay. So I will take 2 and we will go further. Make a screenshot of it. So this is our claim now. With open ball with center P and radius R is subset of U with this radius. Okay, so yeah, we have to prove one set is subset of other. What is the technique? We take one arbitrary point from first set and we prove that it is in second set. So let us start to do. Let x is equal to x1 comma x2 belongs to this open ball, right? See, x lies in this ball, that means distance of x from the center of ball is less than its radius. So that's why distance of x and P is less than R. Okay, that means, so this is this is Euclidean norm. So that's why we write norm x minus P less than R. Implies x means what? x1 comma x2. P means P1 comma P2 less than R. I will skip few steps since many times we have done. You know that how to find norm. So this is square root of, okay, first minus first. That means x1 minus p1 square plus x2 minus p2 square less than R. So you know that the next step is take square of both sides and remove square root. So x1 minus p1 square plus x2 minus p2 square less than R square. Sum of these two is less than R, so that R square, so that's why each of them is less than R square. Okay, less than R square, and x2 minus p2 square, this is also less than R square. Let us take square root of both sides positive. So mod x1 minus p1 less than R and mod x2 minus p2 less than R. So you know that there is one standard result, okay, related to modulus, mod a less than b if and only if minus b less than a less than b. So let us use that result here. What will you get? Sorry, here is square. Okay, so here we will have minus R less than x1 minus p1 less than R, and here also I can write the same, minus R less than x2 minus p2 less than R. Okay, what will I do? I will add p1 in all sides, there I will add p2. So therefore p1 minus R less than x1 less than p1 plus R, and p2 less than R less than x2 less than p2 plus R. Okay, so let us add them. I am going to add inequalities. So see, I will add first inequality. So p1 plus p2 minus R minus R minus 2R. Middle term x1 plus x2. Last term p1 plus this p2 plus R 2R. This thing we are getting. Okay. See, I will call it as equation star. See, this diagram is not required. Now we have understood the meaning. So I will remove this diagram now. And this thing also, it is not required. R is minimum of these two. That means obviously R is less than or equal to each of them. Okay. See, by definition of R, what can we write by definition of R? R less than or equal to P1 plus P2 plus 1 divided by 2, and R less than or equal to 1 minus P1 minus P2 divided by 2. See what I am going to do? I am going to multiply both sides by 2. So that's why 2R less than or equal to P1 plus P2 plus 1, and this is 2R less than or equal to 1 minus P1 minus P2. See what will I do? I will shift 2R on that side. What I am doing, I am shifting 2R on that side and I am shifting 1 on this side. So minus 1 less than or equal to P1 plus P2 minus 2R. Here, what will I do? I am shifting P1 plus P2 on this side. So see, both of them are having minus sign. So if you shift those terms here, we will have plus sign. This is double star. Will you tell me what will you get from star and double star? Star and double star. Will you tell me what will you get from star and double star? See, minus 1 is less than this one, but this one is less than x1 plus x2. It is just like this one, a less than b, b less than c. So that's why I could write directly a less than c. x1 plus x2 less than this term, but same term we have here and which is less than 1. So this is also less than 1. Okay, so it satisfies the condition. Minus 1 less than x plus y. So similarly minus 1 less than x1 plus x2 less than 1. So therefore that point x1 comma x2 belongs to U. Getting the point? We had, since x satisfies the condition of U, that's why we are saying x is an element of U. So we had taken that point from this ball and we proved that it is in U. So therefore open ball is subset of U. Make a screenshot of it and then we will go further. So therefore we proved that we had taken x point from open ball and we proved that it is in U. So therefore open ball with center P with and radius R is subset of U. Getting 9, it is true for any point P, since P was any arbitrary point. So therefore, what can we declare? Therefore, U is an open subset of R2, obviously with Euclidean metric. With Euclidean metric. So in this way we proved it. Okay. So you can make a screenshot of it. After that we will stop. Thank you. Bye bye.